Hello and welcome to Speakeasy JS, the meetup for mad science, hacking, and experiments. I'm Faraz, and I'll be your host this morning. Thanks for joining us. Mad science is about building things that make people say, I didn't know that was possible. So today, we're really honored to be joined by Jordan Eldridge. Hey, Jordan, how's it going?
Hey, good to be here.
Nice. Yeah, so happy to have you. I'm really excited that Jordan's joining us today because it's actually his second time on Speakeasy. And the first time was with Paul hosting. And I was bummed that I didn't get to be here to be the host for your talk. But Jordan is the creator of WebAmp, an in-browser recreation of the classic media player Winamp. And it was from an era when apps used to have skins and they were like a lot more fun and playful. And he also created the Winamp Skin Museum, where you can go and see all the different Winamp skins. And that was actually what his talk was about, the last Speakeasy talk that you can find on our website. So we're just so glad to have you back. And I think today you'll be speaking about something related but different. I think speeding up WebAmp's music visualizer with an in-browser WebAssembly compiler. So it should be good.
Yeah, thank you so much for having me. And I think this has been a really cool space, so I really appreciate getting to be a part of it.
Yeah, thank you for being part of it multiple times now, and it's a lot of work to put together a talk, and also for all your time that you've put into a project like WebAmp. It's one of those things that I think brings a lot of joy to a lot of people. So it's cool that you keep working on it.
Yeah, it's been probably more fun for me than anyone else. So otherwise I wouldn't do it.
Well, that's good. Yeah, the self-motivation helps a lot. That it is really cool. I mean, I recommend if people haven't to check out WebAmp like right now in another tab. It's super cool. And just browse around the skins, and also just the visualizer is so good, which is that's actually I'm super excited to hear how you some of that stuff today, because it's called Butter Churn, I believe, right?
Yeah, so actually I just saw in chat that someone asked my mic volume to turn up. I turned it up a little bit. Just keep sending messages in chat if it's wrong, if it gets too high or too low. Feel free to interrupt with that. But yeah, it's a separate project actually maintained by or built by a friend of mine whose name is also Jordan, and is actually currently in chat helping me adjust my volume here. So the project is called Butter Churn. So it's still so quiet. Are you, Ross? Are you hearing me quietly?
I'm hearing you fine, but let me see. I can also adjust your volume on my end a little bit here. I boosted it. Is that better?
Okay. Yeah. Let's see if this volume works a little bit better. And thanks everyone for speaking up when I couldn't. So Butter Churn is a project by Jordan Berg, a different Jordan, which is a recreation of Winamp's milk drop visualizer. And we eventually did get to meet up. He had worked on it sort of in parallel with me, and we ended up meeting up and being able to integrate his project into my project. And it's been a really great sort of collaboration after that.
Yeah, it's quite good. When I first found it, I was like, this is like the best visualizer I've ever seen. The quality and the detail and the interestingness is very high, which is not true of a lot of visualizers. I had no idea that it was connected to, that you knew him, or that any of the background behind it. But I think I just found Butter Churn one time a few years ago, and I was like, this is so good. But now knowing like how it's all related to what you're doing and stuff, it's really cool.
It's very mad science for sure.
Cool. Well, whenever you're ready to get started on your talk.
All right. I'm good. I don't know if there we go. My slides, my precious slides. All right. So the talk is about compiling to WebAssembly in the browser. And this was like an interesting approach that we were able to find to increase the performance of Butter Churn. So just to clarify, what I'm talking about is we're taking source code in the user's browser, using it to derive a binary blob which represents the WebAssembly, and then sort of instantiating the WebAssembly module there and executing that, which is a little bit different than I think most uses of WebAssembly. So I think we got a little bit of this, covered a little bit in the intro. Butterchurn is a project by Jordan Berg. I highly recommend you check it out. Butterchurnviz.com is the site. That's Jordan's site. And yeah, it's an in-browser music visualizer. And I've learned from the past that it's not good to demo it in a live stream because you really just don't get the sort of like high resolution and like responsiveness that it can deliver. But I do recommend you check it out. Maybe open another tab, butterchurnviz.com. So in the process of writing this compiler, we got to learn a lot about WebAssembly. And I thought, since usually people aren't writing WebAssembly, they're compiling to WebAssembly, we got a little bit of an interesting vantage point. And I wanted to take an opportunity to share a little bit what we learned about WebAssembly generally, and like takeaways from that, as well as what we learned about compiling to WebAssembly and doing that in the browser. So I'm guessing most people who are in this video are familiar with WebAssembly at least a little bit, but I think it's good to just like readdress this a tiny bit, because I think WebAssembly has a little bit been the victim of its own success in that people are so excited about it that it has generated a lot of hype. And with that hype has come some unrealistic expectations about what it is or can do or will do one day. So I'm just going to ground us a little bit in what WebAssembly is. So it's a stack machine. So you sort of push numbers on your instructions, sort of push numbers onto the stack and then consume values off of the stack. It only has numeric types. This is similar to any assembly language. So it's not a high level language where you get like strings or arrays or objects or hash maps. In fact, if you want any of those data structures, you must implement them yourself or compile from something which implements them for you and ship those to your users along with your product code. So this is like something to keep in mind that is easy to lose track of. One aspect where I think WebAmp is actually like underhyped where WebAssembly is underhyped is its sandbox. And I think this has spurned a lot of innovation of using WebAssembly outside of the browser. But it only has access to its own memory. And the only way that it interops with the host environment, so in the browser, that's JavaScript, is via imports and exports that are explicit. So certain values, numeric values that are shared with the host, and then functions which are either sort of injected into the WebAssembly module or exposed from the WebAssembly module out to the host environment. But again, those functions must have numeric arguments and return types, which is a really significant limitation. So now that we understand a little bit what the limitations of WebAssembly are, what is it actually good at? And the real core thing that WebAssembly was created for was code reuse. So being able to take a library that already exists or that is being written to work in some native environment, and to be able to reuse it on the web. So maybe that's a C library, a C++ library, increasingly a Rust library. So that's sort of its main use. But I think because of the performance that you can achieve with it, it's adopted this sort of association with high performance computing, and at least in the sense of the browser. But really the kinds of things that it actually can outpace JavaScript on are relatively limited. It's a testament to how fast JavaScript VMs have gotten, but really you can only get faster than JavaScript in WebAssembly for certain types of workloads. So those are CPU bound tasks which have minimal shared structured data with the host environment. So you can't like pass a large JSON blob into your WebAssembly module and expect to still be fast, or vice versa. And I think this is just worth reiterating that WebAssembly is not yet, or does not appear to be in the near future, ready to be able to manipulate the DOM. And this goes back to like an impedance mismatch between JavaScript being a garbage collected language and WebAssembly being a memory managed language, where you're expecting the code itself to manage its own memory. So now that I've given like my sense of what WebAssembly is, I would like to give a little bit of another introduction to what butter churn is. So as we said, it's actually a clone of Milkdrop, which was Winamp's sort of most famous visualizer. But it's not just a visualizer on its own. It's not like one particular um, like program to map audio data to a particular set of visual data. It's an interpreter of visualizer presets. So users could create these visualizer presets, which consist of their own code in a special language called EEL and some shader code, which would give these really creative like visuals. And so that was sort of the language that the creative people would author in, and they would generate these presets, and then Milkdrop would be able to cycle through them and give you like a wide range of creative, interesting experiences. And Jordan Berg did collect sort of on the order of 40,000 of these presets as a project to assist the Internet Archive. And so you can see we have like a large number of these that we would like to be able to support. And so in the past, Butterchurn handled these presets, which were like .milk files, by compiling them ahead of time to JavaScript and WebGL. And so Jordan wrote a transpiler from EEL to JavaScript, or a compiler of sorts, and then it would evaluate that JavaScript in the browser. But it required pre-compiling all those 40,000 presets. So because we were executing in JavaScript, the math for these presets, we were realizing that the real performance bottleneck was the EEL code, which is like the code that the users would write in their presets, which we were then translating into JavaScript, or Jordan was. And we started to think about how we could sort of fix that bottleneck, because honestly, it did still render very well and at a very good frame rate. But it was definitely like, it would sort of pin your CPU when you went to the site, and like you would get your music and the visualization and like, the sound of a drone taking off from your desk as your CPU heated up and your fans kicked in. And so, knowing now what WebAssembly is very good at, was it a good fit for Butterchurn? And in fact, it's actually like almost a perfect use case for getting the performance out of WebAssembly. So there's minimal shared data. It's really just like some shared values plus a fast Fourier transform representation of the audio signal. We don't need any fancy data structures, really. It's just like math and loops and conditionals. And it's very performance sensitive. We're running basically like hot loops of this code over, over sort of like a grid of the display inside an animation loop. So like performance is really critical. But of course, we have this challenge, right? We're not just like implementing one visualizer. We are interpreting presets. And so this is where we come to the like constraint of needing to do this compilation in the browser. So in a normal WebAssembly setup, you would write your code. As part of your build process, you would compile that to WebAssembly, and then you would ship that WebAssembly down to the browser. But of course, if we don't want to have to recompile 40,000 preset files, we would like to be able to do it in the browser. And in addition, an even more critical reason to do the compilation in the browser is editing. So Winamp offered the ability to edit the presets. It had like a little tiny developer environment inside the visualizer, which is pretty amazing. And so it really inspired people to be owners and creators of their own experience. And we haven't built this yet, but we would love one day to be able to do it. And so that was another big part of our motivation. So what does it actually look like to compile WebAssembly in the browser? So here's an example of this EEL code. You can, I don't know, you might have to like lean into your monitor to see it. But we wrote a little parser to parse this EEL code and then construct an AST out of it. And then surprisingly, the process of actually generating WebAssembly from that is not that complicated. So here's just like a very like small snippet of the emitter part of the compiler. And it seems sort of strange to do something like this in JavaScript where you're like, creating, big blocks of bytes. And it's definitely feels like overkill because like each byte is represented by a floating point number and all these weird things because of how JavaScript works. But the programs are very small. And so you don't need the kind of compiler performance that you would find in a big compiler. It really just has to work and it will be fast enough. And so we took a very simplistic approach, right? This is our like sort of recursive descent emitter. It takes an AST node and returns an array. You can see like the TypeScript types here, an array of JavaScript numbers. We then use that array of JavaScript numbers, put it in a uint8 array, and that becomes the binary representation of our WebAssembly module. And so you can see here, like if you look at line 21, when we encounter a binary expression, first we emit the left-hand side of the expression, right, and get the sort of binary representation of that sub-expression. We emit the right-hand side, get the binary expression of the right-hand side. We find out which opcode we're going to use based on what the operator of that expression is. And you can see like these op.f64 add, you can see in this little inlay here, this is really just a mapping to a number, right? So we're really just building up a giant array of numbers, and that is going to be the code that we can then execute. So in this process, we got to learn a bit about the limitations of WebAssembly and the challenges of WebAssembly. And like I said, we felt like we were really a perfect fit for taking advantage of the performance possibilities of WebAssembly. And still, it was actually very hard to get to a point where we were actually seeing significant performance wins. So some takeaways that we had. So one is that trying to implement trigonometric functions in assembly, very difficult. And that there's a much simpler way, which is basically to shim them. So instead of trying to, generate our own trigonometric functions, either via some compilation process or something like that, we realized, we can just call out to the host environment for those things. They're already relatively expensive, so the overhead there is sort of like not critical. And this ended up working really well. Same for non-deterministic functions. So WebAssembly has a stated goal around being deterministic. And so any source of non-determinism, you sort of need to go get from the host environment. But really our biggest takeaway was just that boundary crossing is really slow. Getting data into and out of WebAssembly from JavaScript is a serious bottleneck, even when you may not realize that it's going to be. So the problem we had was that, like I said, these EEL expressions are getting executed sort of in a hot loop inside an animation frame. And what we were originally doing is we would compile the EEL to WebAssembly, and then we would have our JavaScript host environment sort of run the hot loop. It would like run the WebAssembly function, in a loop. But the way Milkdrop worked is there were a number of like global variables that it would pre-populate before each loop. And they're just like double precision floating point numbers, which is the same sort of representation that JavaScript has for numbers. And so I was optimistic that we would be able to set those values and then read them out afterwards in a relatively inexpensive way, and that the performance win of actually running the equation itself quickly would offset any cost that we were paying. What we found was that was not the case. Writing those values ended up basically counteracting any performance gains we saw from actually the improved speed of the actual equation. So writing the data before we would run the equation to populate, what it can see in the world, and then reading out the results ended up being actually considerably slow. And so we like banged our heads against this problem for quite a while, trying to think of how we could solve it. And we ended up coming up with what I think is actually a relatively novel solution. And so I'm excited to share it with you. So what we ended up doing was making multiple WebAssembly modules. So I said that the cost of going from JavaScript to WebAssembly and vice versa was slow. And you can see here in this code example sort of how you share a value with WebAssembly. You construct a new global, you give it a type, and then you pass it in to the WebAssembly module when you construct it. And then that becomes your shared value. What we realized was, while it's expensive to have JavaScript, to go back and forth between JavaScript and WebAssembly, you can have two different WebAssembly modules share the same global and read and write from it. And use in our like measurements, it seems to have basically no overhead relative, just in the same way that a WebAssembly module can read and write global values as fast as any other value. We found that you can share those values between WebAssembly modules. So what we did was we basically rewrote the code, which was sort of resetting the global values, and the code which was reading out and accumulating the result from the runs. We rewrote that in AssemblyScript, which is like a sort of JavaScript, a subset of TypeScript, kind of. It's like a subset of JavaScript using TypeScript annotations, which can be compiled to WebAssembly. And so we sort of ported little pieces of Butterchurn into AssemblyScript. And so what you end up having is a JavaScript Butterchurn, which has its own sort of WebAssembly module, which is pre-compiled as part of Butterchurn's build. And then the preset gets built in the user's browser. And then those two WebAssembly modules, one pre-compiled, one compiled in the browser, share access to these global values. And with that, we were able to get back to like the sort of performance wins that we were hoping for. I actually was skeptical about any performance wins from the get-go. Jordan Berg was much more optimistic, and he ended up being quite right. So yeah, in the end, we were able to see some significant performance wins. You can see here that, originally the EEL portion of the code was taking about 4.2 milliseconds per frame, and we were able to get that down to 2.3 milliseconds per frame. And this is like the average absolute duration. The way the averages work out, if you look at the average speed up across the sort of sample of presets that we were using in our benchmark, we saw about a 73% speed up, average speed up across all those presets. So that was like a really big win, I think. And it also, having this model where we were porting some pieces of Butterchurn itself into AssemblyScript also opens the door for a lot more performance optimizations, where we think we can pull more and more of the sort of host code into WebAssembly, avoid more and more boundary crossing, and increasingly take advantage of the WebAssembly performance for Butterchurn's own code, which is also relatively math heavy. So yeah, this approach of compiling to WebAssembly in the browser, like when does it make sense? It's like a very, I feel like the stars really just aligned to make this the right choice. But it was like super interesting and fun to do. And I definitely feel like it fit with the sort of vibe of mad science of like, well, you wouldn't really think that you could do that. So when does it make sense to do this? It makes sense to do it when input is dynamic, right? You can't pre-compile the code to WebAssembly. When performance is critical, right? If the performance for this weren't critical, I would probably want it to look at something like an interpreter, where we interpret it in JavaScript, or maybe compiling it to JavaScript, or there are lots of other options when performance is not that much. There's not that much pressure on performance. Again, to take advantage of WebAssembly's speed up, your work needs to be CPU bound, basically, and have minimal shared data, structured data with the host environment. You can share sort of blocks of memory, but if you anticipate needing to like make sense of that as something more than just a block of memory, you're going to end up probably offsetting any performance wins you find with WebAssembly. And finally, I wish I had a little bit more time to go into this, but my original motivation for this project was not, in fact, performance. It was security. So with our previous method where we were pre-compiling to JavaScript, we then had to eval that JavaScript. and that JavaScript then was evaled in the same, we couldn't do that in a web worker to get any kind of security boundary because it had to be fast, and we couldn't, take that message passing overhead. So we were having to evaluate JavaScript in the same environment as WebAMP, which was preventing us from doing things like Dropbox integration or other things where people might pull in sort of security sensitive things into that JavaScript environment. So another big win was the fact that now this code is running in a sandboxed environment with only access to the functions that we inject into it. And those are all pure functions, basically. And we cherry pick out a few numbers, and it's really hard to imagine even the most malicious code being able to to do anything with that. So those were our takeaways from this project of compiling to WebAssembly in the browser. As Faraz said at the very beginning, this was part of my other side project, WebAMP, which is a recreation of the classic MP3 player Winamp in the browser. And having Butterchurn integrated has really completed the puzzle for me. And I'm just so thrilled with what a cool project it is. It was really cool to get to find a way to help it out and help it get a little bit faster. This is a little bit about me. If there's anything here that sounded interesting and you'd like to stay in touch, I'm Capt Baritone on Twitter. There's a little playground where you can play with the compiler at eel.capt.dev. There's also a link to the GitHub repo there. And Jordan and I hang out in the WebAMP Discord, which you can find at webamp.org/chat. And just finally, a big shout out to Jordan for all of his work on Butterchurn. It's just been such a cool project to get to be a part of.
Thank you so much, Jordan. That was amazing.
Thanks.
Yeah, totally. Yeah. Now's the time for people to ask questions. If you have questions, you can post them in the chat and I'll relay them to Jordan. But that was super interesting. Especially the idea of host WebAssembly that is precompiled combined with in-browser WebAssembly that is untrusted, and then having the two share memory so you don't have to cross the boundary. That is super interesting. I've never heard of anything like that, and it's good to know that you can do that with two modules. I haven't played with WebAssembly very much, so that was super fascinating.
Yeah, it's sort of an unusual, you wouldn't usually need to do that, because if your WebAssembly is precompiled, right, you could just move more of your code into that precompiled WebAssembly. And so there wouldn't need to be two modules. You would just add more stuff to your existing module. But because one of them is dynamically derived, we needed a different solution because we couldn't glue them together. And actually, there's a little bit of a funny story here, which is when we first had this idea of could we have two modules? We didn't yet have any experience with assembly script or any tooling set up to compile it. And so what we did was we actually wrote that glue code in Eel and compiled it in the browser as well, just to test it out. So we wrote the thing which eventually became precompiled. We actually would just compile on the fly using the compiler we had written, because we're oh, we need some way to generate WebAssembly. Oh, we have a really cool tool already present to do that. And so for our initial explorations, we just wrote it in Eel, which was a little bit silly.
That's really funny. So I mean, yeah. So what was the reason you went away from that approach? Was that just a little bit minus the Eel part? Could you actually do a thing where you took user input of some form, say straight up assembly script, and then combine it with your own assembly script, and then compile it at runtime if you needed to? Could that or is that just too slow?
Can you say that again?
Oh, I guess I'm just wondering, if you that first prototype you did where you were doing you were compiling basically the host WebAssembly and doing that at runtime, was the main reason you went away from that it was too slow, or is it just because you didn't want to write it all in Eel?
Yeah, exactly. It wasn't too. I mean, it might have slowed down startup because it had to do a little extra work at startup. But really, the reason was the performance was fine. In fact, the main reason was we anticipated that we would want to pull more and more of the Butterchurn code into WebAssembly, and Butterchurn's already written in JavaScript. And so porting it to EEL is like, oh, we have to like figure out how to write this in EEL, and like it's not really the right language for it. And so it was really about sort of setting ourselves up to be able to port more and more over. And since AssemblyScript and is already sort of like a subset of JavaScript, porting existing Butterchurn code to AssemblyScript is actually pretty straightforward. You sort of like copy it over, add some types, and then work around a few other limitations.
Interesting. And what made you think that or what made you want to do this EEL to? So let me just confirm. It goes EEL, and then that compiles directly to WebAssembly. That's the thing that you wrote. Was there anything? Was there any kind of like intermediate thing that you could have compiled that to instead? Like, could you have gone EEL to AssemblyScript and then used some existing package to do AssemblyScript to WebAssembly in the browser? Like, I'm sure there's something written in JS that could do AssemblyScript to,
Yeah, there's a lot of, I think this is another like aspect that makes this project unique, and why like you wouldn't normally end up getting to write actual like WebAssembly bytes, right? In most cases, in a compiler, if you're taking a novel language that you want to compile, you just write like the front end of the compiler, and then you take some pre-existing backend and use that to generate the actual byte code, whether that be WebAssembly bytecode or assembly or machine code. And it's possible that we could have done that, but I think our concern was we wanted it to be much more lightweight than that. We didn't want to like download a huge tool chain into the browser if we could avoid it. And since the language is pretty minimal, we decided to do that. Now, I think there is one downside, right? It's like existing compiler pipelines do have built into them a lot more smarts, right? Things like optimization passes and things like that. So we did miss out on that, but I think the language and the code is simple enough that it wouldn't have provided that much value.
Yeah. Also, it just sounds like from an understandability point of view, it's really nice that you can like look at this compiler and understand exactly what it's doing, instead of a massive tool chain with like a bunch of passes. And I don't know. I really value understandability, so I kind of get like I would probably done what you did.
Yeah, and I think also just the like amount of JavaScript you need to download into the browser in order to make it work. That's like a thing that would, I don't know, like it would bug me to know that I was like downloading all this extra JavaScript to do something.
Yeah, totally. So has anyone else done in-browser WebAssembly compilation? Obviously not from EEL, but from some other language. Is that like a thing that's common, or have you seen it before?
Yeah, I think the other like place where I would imagine it exists, I don't know if I've like, is basically like compiler playgrounds or other places, other kinds of code playgrounds where you want to be able to write in some language and then evaluate it. I don't know of anyone else who has done it as part of like a user experience. Because like I said, sort of our main motivator was like this future idea of putting in an editor, right? So I think that's sort of the core thing, is like when the code itself can be dynamic, that's when it really starts to make sense. And I think that is where I would expect to see it. But I'm definitely sure that there are places where like you can write like Rust and it will like compile it. I don't know whether those ones are doing it on the server. Maybe they are talking back to a server. Certainly, I believe that you can compile Rust C itself to WebAssembly. And so I guess that's another thing to point out, is that we wrote it in JavaScript. I also did an exploration where I rewrote it in Rust, the compiler. Like once I'd written it, it was like sort of easy to rewrite in another language. I was like, oh, this will be great because it'll be like faster or whatever. It turns out, even if it is faster, the binary size of the WebAssembly representation of the Rust compiler, this is a compiler written in Rust that compiles EEL to WebAssembly. The like binary size of that was just like, bloated, and I couldn't really get it down to a reasonable size. So we ended up not pursuing that.
Makes sense. So I guess I'll go to the audience for our final question. WebAmp looks and feels great. Are there any other new features or updates that you'd like to do? What's next?
Yeah. Let's see. I'll spoil a little bit. So this is like not yet announced. This is very experimental, very mad science. Can I share my screen?
Yeah.
Let's see. Let me grab a new browser here. So the next big task is what are called modern skins. So like one of WebAmp's like interesting things is that it can render the actual like quote unquote skins of Winamp, but it can only do the classic ones, not the freeform ones. So the thing we're working on now is quote unquote modern skins, which is like 2000s, early 2000s modern, but they're free form. So instead of just being a collection of sprite sheets, which will be like laid out in the correct place, this is like a zip file containing XML and bytecode written in another proprietary language called Mackie, which orchestrates that XML. And so it's very similar to like JavaScript and HTML, right? You have the XML expressing what the sort of DOM nodes are, and the Mackie defining the behavior of what happens when you interact with them. And so this is like our very, 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 very early prototype of just one single skin. Of course, there are thousands of them. But you can see we already have some things working like animations, right? Actually, let me make this a little bigger here. If I hover over this, we get like this animation that's defined in Mackie. If I click on the volume, like you can see it's animated. You can like slide out panels or like change the color. Let's find a nicer color.
Someone in the chat is saying they can only see your final slide. So I'm going to try stopping and starting the video for a second. Hopefully this fixes it. Okay.
Yeah, let us know in chat if you're having trouble see it. So yeah, this is sort of like the next stage is interpreting the sort of quote unquote modern skins. And so all of this is behavior defined in the skin itself that we're just like interpreting in the browser. And so, this one skin happens to work, but you can imagine that.
Jordan, sorry to interrupt. Do you want to stop sharing your screen? You want to stop sharing your screen and then start again just to reset it? Because I think people can't see it.
Oh, I bet I know what's happening. Hold on. I bet I have multiple. I wonder if I have multiple.
I was seeing it fine on my end. I think it's actually, it seems like a bug in the streaming service we're using because I saw it fine in the editor, but the stream it's creating is wrong.
Got it.
Yeah. Okay. Here we go. I see it again correctly. We'll see what the chat
says.
Okay.
Thank you. Yeah, because it's definitely important to see it. So this is our initial exploration of rendering quote unquote modern skins, and you can see that like all of the behavior of this particular skin, and again, this is just one skin that we're correctly rendering, or not even correctly, partially rendering. And all of these behaviors are starting to work as we build more and more of the engine. So yeah, this is like unannounced. It may never ship, but there's just like so many cool things that are like potentially available. If we can get this to work. So it's been really fun as well. That's sort of the next. If there is a next thing for WebAmp, this will be it.
Nice. Thanks for showing that to us. It's always nice to see live demos too. So that was
unprepared live demos. I'm glad it didn't fall over horribly.
Nice. Well, I think that's all the time we have for now. But thanks so much for bringing that to us here and sharing it with us, and also just for your constant work on such a cool project. I love seeing these kinds of things released into the world. It makes the world more wonderful and delightful. And yeah, your work is always like that. So yeah, thank you for making the world better, honestly.
Thank you very much. And thanks so much for creating this venue. I've been such a fan of seeing all the different talks. So it's really, I really appreciate all your work there.
Cool. Yeah, thank you.